similar. And we cannot in this system write down huge numbers. And it is not clear how, for example, to divide this number by this number in this numeral system. Probably people using this and system we cannot write in down numbers, even did not know about division. Huge numbers we do not know, and it is not clear how, strangely enough, to divide this number by this number in this numeral system. Nowadays in Amazonia there is a tribe of Piraha, and they use only we cannot write in down numbers, right? So one about huge numbers to express numbers one and clear how, strangely enough, to divide even this number by this number in this numeral system. Nowadays in Amazonia there is a tribe of Piraha, and they just only we cannot and such a system right so well about is the same result to express and numbers not clear and how strangely enough to divide even this number by this number this numeral system. Nowadays in Amazonia there is a tribe of Piraha, and they just only we cannot and such a system right so well about is the same result to express and numbers not clear and how strangely enough to divide even this number by this number this numeral system. Nowadays in Amazonia there is a tribe exactly the same situation. On the other hand, we know that if many is substituted by numerals 3, 4, and 5, then we are able to avoid this strange kind of records. So probably by introducing more numerals that can be used to express different infinite numbers, we can avoid this kind of situation. And it is interesting that close to Piraha in Amazonia, there is another tribe, Munduruku, that is able to distinguish numbers up to 5, and they have too many, some not many, and many really many. And this again is very close to the arithmetic of cardinals of Cantor. So you see, if you substitute some not many by Aleph 0 and many really many by Aleph 0, then you have the same result. And I remind you that we have the Cantor set theory in the foundations of the modern mathematics. So this advises us that introduction of more different infinite numbers could allow us to avoid this kind of records and to make our results more precise. So it is clear that methodology of working here that we are going to start to discuss is different with respect to the traditional methodology applied for working with finite numbers. So we would like to introduce this methodological postulate. So we postulate existence of infinite and infinitesimal quantities, but also we accept that human beings and machines are able to execute only a finite number of operations. So a priori, we accept that we shall never be able to give a complete description on infinite process and sets due to our finite capabilities. And this means also that we accept that we are able to write down only a finite number of symbols. Now, the second methodological postulate comes to us from physics. In natural sciences, when a physicist looks in a microscope and observes two dots, he or she does not say that the object of the observation is two dots. He or she says that with this microscope and this lens, I observe two dots. So they talk about what they observe and not about the object, because they perfectly understand that there exists object, instrument of the observation, and the researcher. And we are not able to touch directly the object. We need an instrument. In fact, probably if we substitute the first lens in our microscope with the second one, then the first dot will be visible as 10 dots and the second dot as 15 dots. Again, can we say that this is our object? No. 10 dots and 15 dots are results of our observations with the second lens. Now, a natural question arises: which answer, 2 dots or 10 and 15 dots, is correct? Both, but with different accuracies. So physicists always, when they give an answer of an observation or a measurement, give also the accuracy of the used instruments. We will do the same. We will follow natural sciences, and we shall not tell what are the mathematical objects we deal with. We just construct more powerful tools that will allow us to improve our capacities to observe and to describe properties of mathematical objects. So we always will separate mathematical objects with the tools used to study objects. And we accept that different tools will give us results of observations with different accuracies. So what are our tools? What mathematicians use like tools? Mathematical languages and numeral systems, among other tools. So we will concentrate, in fact, on numeral systems, systems allowing us to express numbers. So we have already seen that these records, many plus one equal to many, is the result of the poor numeral system. So we should, in some way, to be able to register that if we add 1 to an infinite quantity, we should have more than the previous infinite quantity. Obviously, we cannot use these symbols. We should introduce some other numerals to work with them. By the way, Euclid, in his common notion 5, has formulated like the part is less than the whole, and we will use this principle in all our counting. And we adopt it for working with all numbers, finite, infinite, and infinitesimal, and with all certain processes, finite and infinite. Now, I would like to say that in mathematics, numbers are introduced in logic like the result of the operation of 1 plus 1 plus 1 plus 1. However, when people count, they count in more complex ways. They not only add unities, they also often use different units of measure. They subtract from a given quantity, or they divide a given quantity in its parts. And now I would like to show you a way of counting that exists on the Earth for thousands of years, but strangely enough, it has not been formalized in mathematics so far. And I will try to convince you that this way of counting is much simpler and much more powerful with respect to the traditional ways of counting. Okay, this is exactly what I was saying on this slide, what I have just said. So let us consider this example. So suppose that we are in a granary and the owner asks us how to count how much grain he has inside. Obviously, people are not able to count seed by seed because there are too many objects. And the question arises how such enormous number of objects to compute in a reasonable time. Clearly, we can say that there are many seeds in the granary. This is the correct answer, but its accuracy is very low. So in order to overcome this difficulty, people take sacks, fill them in with seeds, and count the number of sacks. Obviously, we suppose that all sacks, in this example, all sacks have the same measure, and all seeds have the same measure, and each sack can contain the same number of seeds. unknown for us, because we are not able to count even how many seeds there are in a sack. If the granary is huge and it becomes difficult to count the sacks, then trucks or even big train wagons are used. So again, we do not know how many sacks there will be in one truck, but we know that each truck contains the same number of sacks. And we do not know how many trucks will be in one train wagon, but we know that each train wagon contains the same number of trucks. So at the end of counting, we obtain a result in the following form. The granary contains 17 train wagons, 12 trucks, 15 sacks, and 54 seeds of grain. Look, this answer has the accuracy of one seed, because now we can, for example, add one seed, and we will see that we have not 54 seeds, but 55. If we subtract one truck, we will see that we have not 12 trucks, but 11 trucks. So we have obtained the result with the accuracy of one seed of grain. Let us discuss this example a little bit more. So in this example, it was necessary to count large quantities, even though they were finite, but people were not able to count them using elementary units of measure, seeds. And so they have introduced new units of measure and behave with them as this new unit of measure were infinite. So these new units of measure are sacks, trucks, train wagons, and it is possible to continue. Thus, it was impossible to formulate the answer in the terms of elementary units of measure, but it is perfectly expressible in the newly introduced system of counting. And I would like to stress that we do not count how many seeds are in a sack. We are not able to do this because there are too many. We do not count how many sacks there are in a truck, how many trucks there are in a train wagon. So each new unit of measure contains a certain number ki of previous units, but these numbers ki are unknown. In spite of this, we are able to introduce these new units of measure and to express the desired quantity by these new units of measure. So it is clear now what I would like to do. I would like to extend, to generalize this way of counting with huge but finite numbers to infinite quantities. So let us do it. We will introduce more numerals. We will enrich our language. So we have introduced our postulates, and as a result, we are not able to use such concepts as bijection, numerable sets, continuum, and to use these symbols. Analogously, when we pass from Roman numerals to the positional numeral systems, these symbols are not used. However, there will be no any contradiction between the new way of doing and the traditional one. The situation will be exactly like with the microscope or telescope, if you like, with the two lenses. There is a lens of Cantor, there is a new lens, and I will show you that the new lens in certain cases allows us to obtain more precise result. So how will we do this? You know that there exist axioms for real numbers, and we will add a new axiom of the infinite unit. It will be expressed by this number, one so-called, called gross one, and it is introduced as the number of elements of the set of natural numbers. And it is defined through its properties. So this is exactly the same way how we move from natural numbers 1, 2, 3, 4, 5, and so on, to integer numbers, where there are naturals and also 0 and -1, -2, -3, and so on. So how people do this? They take axioms for natural numbers and they say there exists an object called 0 and expressed by this symbol. Operations with this symbol are like this and like that. And then we obtain a nice and powerful arithmetic with integer numbers. Here we'll do the same. We introduce this symbol and we'll show how to work with it. So first, property is very simple. This property is infinity. So gross one is the number of elements of the set of natural numbers, it is infinite, so it should be larger than any finite natural number n. Then gross one is a number, so 0 multiplied by gross one is 0, gross one minus gross one is 0, and so on. I'm telling this because when we work in the traditional analysis, we have indeterminate forms of the form infinity minus infinity or 0 multiplied infinity and so on. In our analysis, we'll avoid this kind of indeterminate forms. Analogously, when we have introduced 0, we have avoided indeterminate forms of the kind 3 minus 5, because we are able just to compute directly without any problem in this way. Now, the most interesting way of counting and the property is divisibility. So think about the set. This is the set of natural numbers. Think about it like about our SEC that has gross one seeds. So the set of natural numbers we postulate has gross one elements. Then we postulate that this set can be subdivided in 2 equal parts, and each of them contains gross one divided 2 elements. Pay attention, we are not able to count 1, 2, 3, 4 elements of these 2 sets, because due to postulate 1, we are able to execute only a finite number of operations, and these 2 sets are infinite. Here we apply in the strong form postulate 3. The part is less than the whole. Here we say that half of the set of natural numbers is exactly 2 times less than the whole. So we are not able to count how many elements there are in the set n. We are not able to count how many elements there are here and here. But we are able to say that in our SEC there are 2 times more elements than in half of the SEC. So we apply, as I promised you, people count in a more complex way than just adding 1, 1, 1, 1, 1. Here we take the whole and we subdivide it into equal parts. And then it is possible to subdivide it also in 3 equal parts. And each of them will have gross one divided 3 elements. These sets will be very useful for us. So what is this? This is the third part of the set of natural numbers starting from 1. 1 plus 3, 4, 4 plus 3, 7, and so on. What is this set? This is the third part starting from 2. 2 plus 3, 5, 5 plus 3, 8, and so on. And in general, we suppose this is that the set of natural numbers can be subdivided in n parts of this kind, and each of them contains this number of elements. We can immediately start. By the way, so I have shown you how to compute. These ways of computing have been studied by professional logicians, showing that it is not contradictory. And also it is possible to see who is involved in non-standard analysis stuff, why what I'm saying is not non-standard analysis in this paper. Okay, now let us measure infinite sets. It becomes extremely easy. For example, how many elements there are in this set? It is easy to see that this is the 5th part of the set of natural numbers starting from 2. 2 plus 5, 7, 7 plus 5, 12, and so on. So it has this number of elements, gross one divided 5. How many elements we have in this set? Also easy. This is the 10th part of the set of natural numbers starting from 3. 3 plus 10, 13, 13 plus 10, 23. So it has this number of elements. And we are able easily to execute set theoretical operations with these sets and to compute the result, how many elements there will be, for example, here in this set. This is easy. Intersection of these 2 sets is empty. This is easy to show. 2 belongs to the first set, 3 to the second. So what we have done, we have added 2 new elements. So the first set, this one, has gross 1 divided 5 elements plus gross 1 divided 10 elements, because this set has gross 1 divided elements, plus 2 new elements. So this is the result. And we can write down in the interpret many other numerals. For example, what is this? Gross 1 minus 2. From the point of view of the granary, this is the number of seeds in a sac from which we have taken out any 2 seeds. From the point of view of the set theory, this is a number of elements in the set of natural numbers from where we have taken any 2 numbers. What is this? This is 6 tracks minus 2 sacs plus 3 seeds. In order to interpret what is gross 1 square from the point of view of set theory, it is sufficient to think about the set of couples of natural numbers, you see. And in fact, this is the first couple, the second, the last one in the line. This is the first in the column, the second, the last one. So gross 1 lines, gross 1 columns, and gross 1 square is the number of these elements. Okay, so we have introduced gross 1 as the number of elements of the set of natural numbers. We extrapolate from finite to infinite this idea that the set 1, 2, 3, n minus 1, n has n elements. So gross 1 is the last. Gross 1 is the last natural number because it's the number of elements of the set of natural numbers. In the same way, in the set from 1 to n, n is the number of elements. So now we are able to observe infinite natural numbers. And if you have a difficulty to accept the existence, this is because traditional numeral systems did not allow us to see these numbers. Again, Piraha are not able to observe numbers 3, 4, and 5 by they are there, these numbers. And if we introduce more numerals, then we are able to work with them. Now, I would like to stress again with this simple example the importance of separation of objects, mathematical objects, and mathematical tools. Suppose that our object is the set of natural numbers and we would like to observe it using a very weak numeral system that has 1, 2, and gross 1. So among natural numbers, we are able to observe only these ones. 1, 2, gross 1 minus 1 minus 2, gross 1 divided 2, plus 1 plus 2, minus 1 minus 2. That's it. And now, dots have a very clear meaning. They represent numbers that are not expressible in this weak numeral system. Now, what will happen if we will execute the operation 1 plus 2? What will be the result? Piraha would say many, but we know that here we have know the numeral many, or quantifier many, if you like. And then we have gross 1 minus 1, and only this. So we are not able to express the answer 3. And the correct answer to the question, what is the result of 1 plus 2, is this numeral system, only with these numerals, is too weak to express the result. We need to express more numbers and to introduce a stronger numeral system. So instead of saying that this is a huge and difficult mathematical problem, we say our instrument is too weak. It is not inadequate for this problem. It is necessary to substitute the instrument. So methodologically, I guess that this is a very powerful idea that physicists have understood more than 100 years ago. So it is not necessary, and it is dangerous. It can lead to ambiguities to identify the used instruments, numeral system in this way, and the studied object. It is necessary to separate them. Now, so we know that from 1 to gross 1, we have natural numbers. Then we have seen also that there exist numbers larger than gross 1. And here there are many of them. So they belong to the set of extended natural numbers. How many elements has this set? The numeral system with gross 1 is too weak to answer to this question, because any numeral system, including the system with gross 1, has its limitation and has numbers that cannot be expressible in this. In fact, when I have introduced this symbol, one circle, this is a prompt that can be gross 2, gross 3, and gross and so on, that can be introduced in various ways. Now, let us return to the computer. We would like to compute to construct a computer, and we will use a positional numeral system to express our numbers, because we need to store in the finite memory of the computer our infinite and infinitesimal numbers. So this is our record, our number, and as in any positional system, it is the sum of different powers of the base, in this case, gross 1. So C are called gross digits, and they represent how many, which part of each of the powers of gross 1 will be included in our number. So gross digits can be positive or negative, and they express finite quantities. Then there are gross powers that are ordered, and also they can themselves be of this kind. Now, in order to understand what is this, let us suppose to consider the first simple situation. We have no positive gross powers and we have no negative gross powers, so all this record is reduced just to this. I remind you that gross 1 powered 0 is 1, so everything is reduced to this. And so we have here just C. And C, I remind you, C, all C are finite. So the finite numbers are just simple examples, particular cases of this record. If we have here finite or infinite positive gross powers, then in our number there can be different parts, infinite parts. If in our number there are negative finite or infinite gross powers, then there can be different infinitesimal parts. So in the finite case, we work in the positional numeral system without thinking about whether there are in our number hundreds or thousands or units. We all elaborate all of them in the same way. Here we will do the same with different infinite and infinitesimal parts. We will not think about, it is not important here, there are infinite parts or not, how many there are. They all are elaborated in the same way. And if there are no finite or infinite parts, then we will have infinitesimal. The simplest infinitesimal is 1 over gross 1, that is inverse element with respect to multiplication. And all infinitesimals are not equal to 0. For example, this number is positive because it is the result of the division of one number, positive number, by another positive number. And infinitesimals also can be interpreted from the point of view of granary, because what is gross 1? It is a sec viewed from the point of view of single seed of grain. And what is 1 over gross 1? Seed viewed from the point of view of the sec. Now, in order to show you how to execute operations, I will show you this toy application. This is an infinity calculator that allows us to operate numerically, so with floating point numbers, with different infinite and infinitesimal numbers. Behind it, there is the infinity computer. So this is only simple operation. I will show you how to compute. Let us start. The first example will be simple. So this is an infinite number because it has this positive finite gross power, and it is necessary to take 14.8 parts of these kinds. We would like to sum up it with another positive number that also will be infinite. Let us compute. So the result is this number. It is infinite number having two infinite parts. If we subtract, the second operand will go with the sign minus. If we multiply, then we have we should sum up the gross powers and multiply gross digits. So we have this infinite number. If we divide, then gross powers are subtracted and gross digits are divided. Obviously, this is a very simple example. Let us make things more complex. Let us introduce a finite part in our number. I remind you that it should have gross power equal to 0, and an infinitesimal part. It should have a negative part. So in this number, we have one positive part, one infinite part, one finite part, and one infinitesimal. If we sum up, then we obtain the result having two infinite parts, one finite and one infinitesimal. If we multiply, all gross powers are summed up and all gross digits are multiplied. So this result is an infinite number having three infinite parts. And if we divide, then we have as a result a number having one infinite part and two infinitesimal parts. So we have a computer and we can use it to solve problems. I will show you just one problem. So suppose that we have a function g of x represented by a computing procedure f of x, and we would like to compute its derivative, but we have no, unfortunately, the computer program to allowing us to compute this derivative. So people use this approximation formula. If we are in mathematical analysis, then taking limits of all these expressions, if f is differentiable, then they will give us the first derivative. But on a computer, this is not the case, because when h becomes very small, then in the numerators we have the same numbers, because the number of digits in mantissa in the computer is limited, and we will arrive to the situation where it is not possible to compute. There are errors. I just illustrate this by using this function, and we would like, it is represented by a computer procedure f, and we would like to estimate using this formula its derivative at the point 3. So here we have forward and backward differences, here central difference. On the horizontal line we have h, and here on the vertical axis we have error. So when h becomes smaller and smaller, then error initially diminishes, but then when this situation with mantissa occurs, what happens? It happens that the error goes to the sky in all these cases. So it is a problem that on traditional computers it is not possible to avoid. What if we go to on the infinity computer? On the infinity computer, the situation is is different, because we can avoid using this dangerous formula. Suppose again that we have this function, it is represented by procedure f of y, and we would like to compute not only the first derivative, but also the second and the third derivative at the same point. In addition, we suppose that we do not know the formula. It is a black box for us. So instead of using those formula, we just evaluate f at the point 3 plus this infinitesimal value. What the computer will do, it will take this number and will assign it to x, and will execute this operation. But for us, it is a black box. We are not able to see this. So what we are able to see, we're able to see only the result. The result is a number having one finite part and several infinitesimals. Now, look what happens. It is possible to prove that if we take 2, then it will be the exact value of the function at point 3. If you take minus 0.5, it will be the exact value of the first derivative. If you take 0.25, it will be the exact second derivative, multiplying it by 2. So, and this minus 0.1 gives us the exact third derivative. So we are able on the infinity computer to obtain exact values of the derivative just by one evaluation of the function. So this is really, really amazing. Now, let us now say a few words. I am close to the end of the lecture about some arithmetical paradox. So suppose we are in the traditional viewpoint, traditional fashion. Suppose that we have x, we multiply both parts by 2, then we add 1 on the left and on the right. So what do we have here? We have x. We can substitute. We obtain 2x plus 1 is equal to x, simplify, and obtain x equal to minus 1. But our x is this one. So you see, traditionally, we obtain this result. Here, there are no errors, that the sum of an infinite number of positive integer numbers is equal to minus 1. Of course, you can say that this is a series and it is possible to do, it is necessary to behave another way. However, this result is considered seriously and as a correct result, because we have done all the traditional steps we do when we work with the finite quantities. In the new fashion, new methodology, what can we say? First of all, this x is not well defined, because we should say how many summands there are in our sum. If they are k, where k is infinite, then our x is defined in this way. When we multiply both parts by 2 and add 1 on the left and the right, now we are able to observe that there exists this number. Since k is infinite, 2 power k is also infinite. And when we go to substitute, we obtain this result. So minus 1 that there was before is visible. But now here there is an infinite quantity that was invisible before. And when we choose different k, we obtain different results. If we choose k equal to gross 1, this is the result. Infinite number. If k is different, then the result is different. Okay. So I would like now to talk a little bit about another paradox that is called Hilbert paradox. So imagine that we are in a hotel, and this hotel has an infinite number of rooms, and all of them are occupied. Then there arrives a new guest in the traditional hotel. Then it is not possible to put inside the new guest because all rooms are occupied. In the Hilbert's hotel, the person on the reception starts to move people. The person from the first room to the second, from the second to the third, and so on. And at the end, we obtain that all people went to the next room, and the first room is empty, and we can put the newcomer to this empty room. So here this paradox. We have supposed that all rooms were occupied, but we we were able to put the newcomer in this room if we make this procedure. Clearly, what will happen in the traditional hotel with a finite number of rooms? If you apply this procedure, then the first room will become empty, but the person from the last room will go out from the hotel clearly. Now, I would like to show you, I hope, now please give me a feedback if you will be able to hear. I would like to show you this cartoon that has been developed at the University of East Anglia in the United Kingdom by Professor Davide Rizza. And before we start, so please say me if you hear the voice, the audio. And so Professor Davide Rizza has developed a web page dedicated
Buenos
to
días, ¿me
teaching
escuchan?
this methodology and also this nice cartoon that I...
Buenos días. Buenos días, mi nombre es Clara Siriaco, yo soy parte del soporte técnico que va a estar manejando esta sala. Interrumpo la conferencia magistral para decirles que me han informado que vamos a iniciar la primera reunión, la primera presentación a las 10:30 de la mañana, debido a que la conferencia todavía no ha terminado. ¿Me escuchan?
Perfecto.
Ok, gracias.
propose to you. Please give me feedback about the sound. Do you hear?
Is on a holiday. He's looking for a room. He arrives at the Hilbert Hotel, but seeing that it has no vacancies, he decides to leave. Wait, a voice cries. Yarrow stops suddenly. It's the hotel owner, Hilbert. Hilbert explains that his hotel has infinitely many rooms. There are as many rooms as there are natural numbers. So even if the hotel has no vacancies, they simply shift the guests to the next room. Yarrow could therefore stay in room 1. Great news! Infinitely many guests plus 1 are still infinitely many. So it has infinitely many rooms. Finitely, it can be specified by number, but you can never specify infinity by number. Yarrow has his doubts. Since the hotel plan uses finite number numbers, as if there is no last room with a finite number. Yarrow believes, since there is one particular infinite number of rooms, it should be possible to specify a last room. And certainly when the hotel was built, each room was given a number. Yarrow, growing skeptical, puts on his spectacles to take a better look. Peering down the corridor, he can just make out a distant room with a gross 1 symbol on the door. Look, he exclaims, and hands his spectacles to the hotel owner. The hotel owner squints through Yarrow's glasses, and sure enough, he spots the gross 1 room. By Jove, you're right. We're actually full, cried Hilbert. It turns out there is an infinitely distant room with gross 1 on it. The room where the furthest guest in the Hilbert Hotel stays. Unfortunately for Yarrow, the hotel is completely full with gross 1 guests tonight. Not to worry though. Turns out a hotel recently opened up nearby with gross 1 plus 1 rooms. A nice little place called Zeno's. Hopefully Yarrow will make it there before nightfall.
Okay, so this is the web page where you can observe this and other material. Now, since the time is finished, I would like just make a small observation regarding again physics of what we are doing. So in physics, the concept of discrete and continuous are relative. For example, is this pen discrete or continuous? It depends on the instrument we use to observe it. If we observe it by eye, it is continuous. If I look by a microscope, I see molecules, atoms, and so it is discrete. So the same object can be visible in different ways. In mathematics, this is not the case because functions, for example, are either discrete or continuous in the traditional mathematics. And what about the new one? So if is this function discrete or continuous? It depends on the unit of measure we have chosen. So we choose how to see our object. If all these distances and these ones are infinitesimals, then the function is continuous and it's possible to talk about order of continuity. If these distances are finite or infinite, then the function is discrete. So we decide how to observe our object. Also, delta function. Traditionally, what is delta function? Is a function which has at a point an infinite value. In one point, in all others, it has valued 0, and the integral is equal to 1. So this is a qualitative description. Now we are able to give a quantitative one because this function has the integral exactly 1, and this is our accuracy. If it is not sufficient, we can consider another delta function. So there is a possibility to construct another kind of analysis, and also physicists use strongly the concept of delta function. So hopefully it will be possible to improve results also in physics. And the last example that I would like to show regards probability. So suppose that we have a disk that is rotating, which is the probability that this dot will stop in front of the arrow. Traditionally, people answer 0, but 0 should be the impossible event, and this event can happen. So this is a kind of not nice thing, because this is an event that can happen, but probability is 0. What do we say in this way? Again, we separate the object from the instrument. We ask, but how many dots are we able to distinguish over these circumstances? So if on this circle you are able to distinguish 10 dots, then the probability will be 1/10. If 20, 1/20. If gross 1, 1 over gross 1, and infinitesimal by positive. So the introduction of this new kind of numeral system allows us to see many objects more precise and to avoid numerous paradoxical situation. I would like to finish saying that there exists this popular book written in a popular manner explaining what we're talking about. And also, if somebody is interested in a more detailed description, there exists this paper that is more than 100 pages, and it is relatively recent. And then there exist these two web pages, this one and this one, where you can take a lot of material. Thank you very much for your kind attention.
Thank you, Dr. Servio, for your excellent, very interesting and didactic presentation. It's
Thank you.
a very beautiful time.
Thank you.
No sé si tenemos tiempo para preguntas o en vista de que ya son las 10:30 no habría oportunidad. I received one question
Yeah.
Okay.
Yes. Yes. Sure.
How the infinity calculator could influence the calculus courses of the first years of university?
Okay, so this is a good question. Clearly, the calculator is just a toy. What can really influence the courses at the university is the methodology and this new numeral system. In fact, I suggest you to go to this site, numericalinfinities.com, where there is a manual that has been already applied in several countries, how to teach this methodology. And there are research tasks with, not research, exercises with answers. This manual has been initially written in English, then translated in Italian, and now people from Argentina are translating it to Spanish. And I'm sure that if you will contact Professor David Eritsev, he will be happy to share with you materials and to help in teaching. In my opinion, this is an extremely important, because this mathematical analysis and this set theory and way of computing allows us to do many things that were either difficult or impossible with the traditional point of view. In fact, on the web page, this way, theinfinitycomputer.com, from there it is possible to download several papers dedicated to teaching this methodology. They were written after making
Buenas, ¿cómo estamos? Continuamos con la segunda jornada, o sea, el segundo día de jornada de investigación científica. ¿Cómo le ha ido, Jairo? ¿Está todo bien? ¿Me escucha bien?
Muy bien, gracias a Dios.
No se escucha aquí.
Sí, te escucho perfecto.
Espérese un segundo. ¿Me escucha ahora?
Sí, te escucho perfectamente bien.
Muy bien. Bueno, Jairo, vamos a empezar con tu conferencia o tu exposición sobre enseñanza de la investigación, una propuesta para la universidad. Algo muy importante en este mundo global, lleno de incertidumbre y que, como tú puedes ver, de pandemia, ¿no? Que está caracterizando el mundo hoy de la virtualidad, como yo le llamo la covirtualidad, porque una virtualidad forzada por el COVID, no la virtualidad normal antes del COVID. Entonces, ya tú sabes que nosotros somos, esto es una exposición presencial virtual y tú como parte del staff de profesores de investigación de la Universidad Adventista Dominicana, de la provincia de Monseñor Noel, de aquí, realmente te damos 20 minutos para tu exposición, así que puede empezar.
Muchas gracias. Para nosotros realmente es un verdadero honor poder compartir con esta audiencia. Un tema sumamente interesante estábamos escuchando en la conferencia magistral, pero vamos a hablar un poquito de nuestra cotidianidad, y el tema de la enseñanza de la investigación en la universidad es un tema que en los últimos tiempos en nuestra región tiene o está mostrando cierto interés. Y por eso nos dedicamos a reflexionar un poquito. La propuesta fue enviada como taller, así que vamos a partir, ¿no?, de algunas reflexiones. Hay una escritora apellido White que escribe sobre educación, escribe sobre la mente. Ella dice que una educación que sea buena, que sea verdadera, debe promover la reflexión personal en lugar de adiestrar la memoria. También ella dice que esa educación da prioridad a la facultad de razonar y juzgar al estudiante por sí mismo. Tópicos interesantes en el contexto pedagógico actual. También dice que apunta hacia la más alta norma de excelencia mental y moral, en lugar de dar prioridad hacia pensamientos indefinidos o una mente indolente. Igualmente, que en lugar de pensar superficialmente, debemos alentar a la observación minuciosa y la independencia de pensamiento. Por último, una educación verdadera debe llevar al estudiante a hacer planes y ejecutarlos, practicar el tacto, la pericia y otras cosas más. Nuestra reflexión esta mañana parte de algunas premisas. Lo primero fue que hicimos un análisis de los programas de asignaturas de investigación en universidades dominicanas y encontramos algunas características. Encontramos que estaban basados prácticamente en contenidos. Se da preferencia a aspectos epistemológicos y teóricos de la investigación. Usualmente, la elaboración de un informe aparece en los programas a final del curso y encontramos asignaturas que el nombre es investigación, que no tenían dentro de sus contenidos espacio para elaboración de un informe. No siempre, mejor dicho, pocas veces, esas asignaturas de investigación se comienzan a impartir desde los primeros semestres. Encontramos programas de planes de estudio que la investigación se incluía ya al final, séptimo semestre. Y falta de integración de la investigación con otras asignaturas. Este último punto no es el tema de hoy, sino que vamos a hablar solamente de las asignaturas propiamente dichas de investigación. Otra premisa de la cual partimos en estas reflexiones es el enfoque de enseñanzas por competencias, el constructivismo, etcétera, y cuya principal característica es que debe estar centrado en el alumnado. Primero queremos categorizar las competencias investigativas, enseñar investigación, pero ¿qué debemos enseñar? Bueno, debemos enseñar a observar, debemos enseñar a preguntar, debemos enseñar a reflexionar, debemos enseñar a proponer, hipotetizar. Debemos dar énfasis a las competencias tecnológicas, siendo que la tecnología nos envuelve y de eso creo que no hay mucho para discutir, estamos conscientes de ello. Debemos enseñar competencias interpersonales. ¿De qué nos vale un buen técnico en investigación cuando no puede trabajar junto a un equipo de investigación? Competencias cognitivas, por supuesto, tanto dentro del ámbito de investigación como dentro del área, el tópico, la disciplina donde se esté investigando. Competencias procedimentales, por supuesto. Competencias analíticas, que bien la podemos unir con las competencias reflexivas, pero estas competencias analíticas son sumamente importantes en el momento de dar procesamiento a la data que recogemos. Y competencias comunicativas. Una investigación que no se comunica no sirve para nada. Mejor que no se hubiera hecho. Enseñar investigación. Creemos que enseñar investigación es posible. Y en este sentido, se debe orientar hacia el uso de estrategias didácticas y actividades diversas. Tenemos que seleccionar bien lo didáctico y las actividades si queremos realmente enseñar investigación. Que pongan al estudiantado en contacto con los diferentes contenidos, pero también procesos. Y que les permitan entonces ir adquiriendo las habilidades y competencias que los califiquen para hacer investigación. En este sentido, López de Parra y otros nos sugieren que la universidad debe impulsar la formación en investigación desde el proceso mismo de aprendizaje del estudiante, no separado a ese proceso, a lo que ellos denominan investigación formativa, no requiriéndose procesos ajenos a la vida común diaria del estudiante mientras está en la universidad. Al enseñar investigación nos hemos encontrado lo siguiente, que nosotros recibimos un alumnado que tenemos que motivarlo. Y estoy hablando específicamente de la Universidad de República Dominicana, pero no es mucha diferencia con otros países de la región latinoamericana. El estudiante viene con un nivel de conciencia, le llamo así, muy bajo en cuanto a lo que es investigación. Parte de esto está en que en la secundaria les dicen hay que investiga sobre los alcanos. Y ellos buscan una información sobre los alcanos, las diferentes fuentes. Al otro día la traen al aula y esa es la investigación. Eso lo hemos visto a través de experiencias de observación directa en varias aulas de clase. Nuestro alumnado viene con una metodología conductista donde se promueve más el concepto, se promueve más el consumismo que la producción. Hay que convencer entonces a ese alumno de que él puede producir. Sí, tú puedes hacerlo. Aún más, hay que convencerlo de que él debe producir. Si vas a estar en la universidad, debes producir. Y hay que convencerlo de lo que es realmente investigación y para qué sirve. En cuanto a la metodología, realmente nos ha funcionado mucho una metodología que le llamamos simple y llanamente taller. Brevemente la describimos así. Damos una demostración junto al concepto que se está trabajando. Por ejemplo, los objetivos específicos de la investigación. Damos la demostración junto con el concepto de objetivos específicos y enseguida le damos la oportunidad al alumno de elaborar sus objetivos específicos de acuerdo a su tema de investigación. Incluimos aquí el concepto de poder bajar los contenidos al hacer del alumno. ¿Qué queremos decir con esto? El alumno va a estar trabajando objetivos específicos, pero es posible que todavía en su mente no tenga claro el concepto. Entonces, él mismo debe ir a la teoría y bajar ese concepto. De esta manera, yo me estoy asegurando un estudiante metacognitivo, que en el momento en que no está bajo la tutela de un docente, él sabe qué hacer cuando no domina algún aspecto específico de la investigación. Todo esto está dentro de los modelos constructivistas y de competencias que buscan lograr que el alumno haga cosas. Y por supuesto, la evaluación se concentra entonces en los productos que el alumno va produciendo, valga la repetición, fruto de este taller. Ahora, nosotros nos encontramos con, como dije al principio, con planes de cursos, programas de cursos muy enciclopédicos. Sugerimos elaborar entonces un cronograma de trabajo durante el semestre que esté basado en la realización o construcción de ese producto final. Para eso, distribuimos los contenidos teóricos en torno a la elaboración de ese producto. Y el docente es tutor durante todo el proceso de construcción. Pero tenemos que apelar al compromiso del estudiante. Hay que comprometerlo. Firmar un contrato con él. En ese contrato tienen que estar las cláusulas bien definidas de cómo va a funcionar ese taller de construcción de una propuesta o un producto típico de investigación. Ahí hacemos énfasis en los aspectos de honestidad. Debo convencer a mi alumno de que si él comete plagio, él no está aprendiendo, además de el aspecto de honestidad, de valores. Por supuesto, ese valor me permite entonces realmente alcanzar las competencias. El curso completo va a girar entonces en torno a ese producto, y ese producto bien puede ser una propuesta de investigación, una investigación a escala, o cualquier otro producto de acuerdo a la asignatura que estemos trabajando. En fin, la meta es lograr que el alumno piense como un investigador. Es lo que nos proponemos. Que el alumno pase de entregar un requisito de una clase a pensar como un investigador. Ahora, para lograr eso, yo tengo que enseñar al alumno a olfatear tópicos, temas, aspectos para investigar en su propia área de desempeño. No fuera de su área de desempeño. En mi clase. Si es un alumno que ya está activo en trabajo, en labor, donde tú estás trabajando. Y otra cosa que nos ayuda mucho a lograr esta meta es abrir durante la clase constantes debates sobre los elementos que se están trabajando en clase. Esta última parte es vital porque estamos trabajando los objetivos específicos de la investigación, entonces cada uno tiene que exponer sus objetivos. Y yo les hago preguntas como docente, como tutor, y les pongo a ellos en un lugar donde ellos tienen que a veces cambiar sus objetivos, pero ellos tienen que cambiarlo de manera consciente. Así que esta parte de dialéctica, de debate, de conversación es realmente indispensable en este sentido. La evaluación del curso. Evaluamos por productos. Si estoy enseñando un curso, por ejemplo, de técnicas de investigación, puedo poner como producto de todo el curso la elaboración de una propuesta de investigación. La evaluación del curso va a consistir en la elaboración y el avalúo y la evaluación final de esa propuesta. Si fuera, por ejemplo, una clase de metodología de investigación en algún área, pues podemos irnos a completar una investigación completa a escala, por supuesto. Pero también podemos adquirir o tener la modalidad de papers o de artículos de investigación, fruto de mi clase de investigación. La idea es que podamos bajar lo más posible al estudiante a lo que es el ámbito investigación y publicaciones en términos científicos. En conclusión, es posible cambiar la forma en que enseñamos la investigación. Creo que como país tenemos que rediseñar entonces los programas de asignaturas y hacerlos más orientados hacia el logro de competencias. Perder el miedo a ¿y qué va a pasar si yo no le pongo a leer un libro sobre hipótesis? Bueno, no le pongo a leer un libro sobre hipótesis, pero le enseño a fabricar una hipótesis. Y cuando necesite información sobre hipótesis, a buscarla de manera autónoma. Adoptar una metodología donde se priorice la elaboración de productos tangibles. Productos finales, como vimos anteriormente, una propuesta, un paper, en vez de muchas partes sin estar articuladas. Debemos evaluar de forma continua y sumativa esos productos. Continua. debo asegurarme de que el alumno va elaborando frente a mis ojos, aunque sea de manera virtual, pero frente a mis ojos cada una de las partes de esa investigación o de ese producto. Y entonces eso me dará lo sumativo. Debo enseñar al alumno a pensar como un investigador. Me he encontrado que gran parte de los alumnos que toman clase de investigación, no voy a decir cómo ellos elaboran sus productos que entregan, pero quieren salir de la clase. Debo enseñarle a pensar como un investigador, lo que me permitirá poder integrar entonces los procesos investigativos en todas las demás carreras y áreas de su plan de estudio. Algunas referencias y muchas gracias. Adelante, moderadores.
Muy bien, muy bien. Jairo, ahorita quiero además pedirle excusa porque estamos en un laboratorio, como dice el tecnológico, y no me presenté. Mi nombre es el doctor Andrés Mereo y soy especialista en filosofía de la ciencia, la tecnología y todo lo que es el ámbito de la virtualidad y el cibermundo. De más de 25 años he estado trabajando en Estados Unidos aquí, todo el ámbito del ciberespacio y las implicaciones políticas y sociales, educativas que se desprenden de esto. Yo creo que parte de tu descripción para que traiga un resultado al alumno en ese proceso de investigación, o sea, construye toda una perspectiva muy importante para estos tiempos. Vamos a seguir entonces con otra intervención importante de lo que es la biométrica, la biomimética de la ciencia y la tecnología, por Visto Castaño, que es del Centro de Física Aplicada y Tecnología Avanzada de la Universidad de México, del campus UNAM. Es decir, que Jairo y Víctor, ese encuentro que están dándose a través del ciberespacio entre dos universidades, una de aquí, de